Okay, so in this set of slides, we are going to see policy gradient methods, which is quite different from value-based methods that you have seen in reinforcement learning till now. Let's dive straight in. All the RL methods that we have seen till now in the course are value-based methods because some notion of value function is always maintained and a policy is derived from this value function. For example, in value iteration, and the value function is iterated continuously till you obtain the optimal value function, after which the optimal policy is derived from that. In policy iteration, even though the policy is directly optimized, value of the policy is always iteratively improved in the policy evaluation step. But now we are going to see that policies can be optimized directly without the need to maintain any notion of value function. The advantage of this method is that we can learn continuous actions, which is not possible in value-based methods. For example, in the Q function, and for example, in the Q learning algorithm, we had this estimate of Q function, which included the state and the action. Now, if we have to maintain a Q value for every action of each state, then if we have continuous actions, this representation goes exponentially large. But if we do not need to maintain any estimate of the value, then we can do continuous actions. We can model continuous actions too in reinforcement learning. So Q learning, that is a popular reinforcement learning algorithm, is a model-free value-based method where no policy representation is used. The policy gradient, on the other hand, which we will see in this set of slides, is also a model-free method, but this is a policy-based method where there is no value function representation used. Till now in this course, we have almost always seen a deterministic policy. A deterministic policy returns a deterministic action for a given state. But from now on, in this set of slides, we are going to be looking at stochastic policies, which will return a probability distribution and over the actions for a given state. We are going to use a function approximation, and this function true policy pi has been approximated using function approximation, and we obtain a new policy pi, which is parameterized by this variable theta. Now, in reinforcement learning, there are two kinds of situations that we can encounter. Either our environment can have a discrete action space in which every state has a set of discrete actions that the agents can take, or the agents or the environment can be of the nature of continuous actions, where at a given state, for a given state, any one of a large number of continuous actions can be taken. Now, if our environment has a discrete action, it is common to use a softmax function to model the stochastic policy. In a softmax function, we have a function like h. Think of that as a scoring function, which is raised to an exponential, and it's divided by the sum of all exponentials of every action a prime, and this will return a probability distribution that can be used for the stochastic policy. So the stochastic policy can return a distribution given by this expression. The scoring function h could be linear or non-linear in theta. So this is a function that is approximated using the parameter theta, and therefore it can either be linear, where we could use a linear function approximator, or it could be non-linear, where we can use an approximator like the neural network. So if we need to model continuous actions using a stochastic policy, traditionally some kind of a continuous function like the Gaussian function is used. There is a good reason for why we need to use stochastic policies in policy gradient. Now, when we need to take a gradients for some functions, it is going to be very easy for us if this function is a continuous function. Now, if we have a discrete policy which returns a discrete action, this is a discrete function, and taking gradients for discrete function is not straightforward. Now, when we model this as a stochastic policy, the policy will return a probability distribution which can be thought of as a continuous function in the range 0 to 1. The objective in reinforcement learning is to maximize a discounted sum of rewards. In this expression here, we have the Monte Carlo estimate Gn, which is the discounted sum of rewards that you will get over infinite horizons. The gradient update rule here is given by this equation. In policy gradients, the current policy is iteratively improved at every step till we reach the most optimal policy pi star. During the optimization step, we consider the log likelihood of the policy and take a gradient of that log likelihood, multiply that using the Monte Carlo estimator Gn, and take a step in that direction using the step size parameter alpha n. In the upcoming slides, we are going to be seeing a derivation for this update rule. Now we see the well-known policy gradient theorem in reinforcement learning. The stochastic policy gradient theorem shows that the gradient of the value function is directly proportional to the summation over mu s, which is the stationary state distribution, and the summation over the actions of the approximate q function q pi theta sa, and the gradient of the current policy pi theta. Now we are not going to go through the derivation of this stochastic policy gradient theorem, but if you're interested, you can have a look at the derivation in either the Sutton textbook or in some other source online. The reinforce update, which is the update that we just saw a couple of slides earlier, can be derived from the policy gradient theorem. Now we start off with the policy gradient theorem, where the gradient of the value function is given by this expression on the right. So this expression is just substituted into an expectation, and where the expectation is over the policy pi, and we remove the first parameter, which is the first term over here, which is the summation over the steady state distribution. In the second step over here, we introduce a term pi a given Sn a, and we multiply and divide by this term. Now we can see that this term summation of a pi q pi can actually be written as q pi Sn a n. This is because when we sum over all the actions and multiply the q function by the probability, now if we have a system which returns a very high probability for the right action an, then almost that probability will be very close to 1, and the probability for the other actions will be very close to 0. In the next step, because we know that the expectation over pi of q pi is actually the Monte Carlo estimate Gn, we plug in this value. Then we see that if we just use the log of the policy, this expression is equivalent to this fraction here when we take the gradient. So hence, using these steps, we can see that the stochastic gradient at time step n is given by this expression gamma n Gn and nabla log pi theta, which was the gradient update we saw 2 slides back. So there are some critical limitations when we use this kind of a technique for doing policy optimization. Now, because we are using Monte Carlo samples, the variance can be very high. You might have seen that Monte Carlo samples will have a high variance earlier in the course, because now we are doing a complete sample of the entire trajectory before we optimize the policy. Now, like I just said, each update sees a large step for the Monte Carlo estimate. Therefore, the variance can be quite high. So, because of this critical reason, in practice, the reinforce algorithm using the gradient update that we just showed has a very slow convergence. One possible solution that has been illustrated in literature is to use a baseline with the reinforce algorithm. So there is a subtle difference between the update rule for reinforce with baseline as compared to the traditional reinforce algorithm. Now notice that we can substitute the previous expression for reinforce, where we just had a q pi, with this term here, q pi minus bs, where bs is some baseline function. Now this can be done because this new term that we introduce here is actually what we have written out here, which is summation over a bs, the gradient of pi a given s. Now this summation term can be taken inside the gradient, and because the summation over a for all the actions for the policy pi is actually 1, and we get the gradient over 1, which is 0. Therefore, this new term that we introduce is effectively 0. Therefore, this new update rule that we have here introduces a new function which is known as the baseline function, and in addition to the Monte Carlo estimate Gn. Now, because we subtract the Monte Carlo estimate using this additional baseline function, the problem of variance has been shown to be much lower than the traditional reinforced algorithm in practice. In practice, we most commonly use the current value estimate Vpi as the baseline function BFS. Another class of problems called actor critiques will use a separate function called advantage function as the baseline. We will see actor critiques in the later part of this course. So reinforce with baseline shows a faster convergence than reinforce in practice. So just to summarize what we have seen so far, the update rule for vanilla reinforce algorithm is given by this expression, where we take the gradient of the log likelihood of the policy and we multiply that with the Monte Carlo estimate Gn. On the other hand, for reinforce with baseline, we will replace just this Monte Carlo estimate Gn and with this term Gn minus a baseline over Sn. Now, I have not listed out all the steps for the reinforce and the reinforce with baseline algorithms, but you can always look up the pseudocode from the Sutton textbook. But the most important part of both these algorithms is just this update rule, which we have derived and clearly seen in this set of slides. In the traditional grid world example that we normally see in reinforcement learning, it has been shown that the reinforce with baseline converges much faster than the vanilla reinforce algorithm. This performance graph shows the effectiveness of reinforce with baseline over the traditional reinforce algorithm. So this graph shows the Monte Carlo return G0 on the y-axis and the episodes on the x-axis. To conclude, we have seen that policies can be optimized directly without value functions, without any representation of value function in reinforcement learning. The advantage of this method is that we can extend reinforcement learning to continuous action spaces. Policy gradient methods use parameterized stochastic policies because that allows the method of gradient descent to be used to update the policy parameters. The reinforce algorithm, which is a popular policy gradient method, uses the Monte Carlo return for the policy update. On the other hand, the reinforce with baseline algorithm stabilizes the reinforce algorithm further with a baseline.